MO theory explains it all, or, at least some things. What we're going to look at in this video is a little bit about bonding, right? How we can predict our bond order for a variety of different diatomic molecules, and also paramagnetism, which we didn't explain too well. Still to come later is a more thorough discussion of resonance, but we won't quite get there this time, so we'll put that in a box. But let's see how MO theory can be used to explain these other theories. All right, bond energy, bond order, bond length, magnetism, paramagnetism, diamagnetism. How does it all come together, and what does MO have to do with it all? So what we've got over here is a diagram that shows us both our MO diagrams with no mixing and, with mixing, and our MO diagrams without mixing. So here we've got boron through nitrogen and then oxygen through neon, and how those all fit together. Now what we showed here is just the filled MO diagrams, but you can imagine as I go from diboron to dicarbon, I add 2 electrons. So I add an electron in each one of these to get that, right? As I go from carbon to nitrogen, I add 2 more electrons, so I fill up this box. I go to oxygen, I add 2 more electrons, so forth and so on. So that's you can build an individual MO diagram and use the atomic orbitals to get to them for each one of these, and I encourage you to practice that, but we're going to start with just these filled diagrams right here. All right, now we can see a couple different things happening here. All right, so we can see here we've got our sigma 2s and sigma 2s star, always going to be the 2 on the bottom, but what comes next depends on whether we have mixing or not. Whether we've got the pi 2p that we see here when we have mixing, or the sigma 2p when we have no mixing. That doesn't matter a ton down at the bottom, except that it is one of the reasons that we see paramagnetism in diboron, but not in dicarbon or dinitrogen, right? Here, everything's paired up. This is what explains why oxygen gas is actually paramagnetic, and this is actually a really cool demo you can do if you liquefy it, so you get the oxygen gas really cold. It has 2 unpaired electrons. So paramagnetism comes from having unpaired electrons. In the MO diagram, oxygen actually has 2 unpaired electrons because of the order of the orbitals, and we can see that it is in fact paramagnetic. All right, we can also take a look at bond lengths and bond energies. Remember, those 2 are going to fit together. And as we move from boron to carbon to nitrogen, we can see we go from a bond order of 1 to 2 to 3, right? Because we have our bonding minus anti-bonding electrons. The one thing I will point out here is that these bottom 2 always kind of cancel each other out, right? The sigma s star, the sigma star 2s and the sigma 2s. So we can kind of just look at these ones up above to figure out the bond order. So boron has 2 electrons in bonding, carbon has 4, nitrogen has 6. All right, so we go from 1 to 2 to 3 in terms of my bond order. And in fact, nitrogen, if we look at molecular nitrogen, has a triple bond, right? So there's our bond order of 3. And the bond energy goes up as well, from 290 to 620 up to 945. And why? Because there's a lot of more electron density holding it all together. A lot of bonding interactions are going on there. Now from there on out, things start to get weaker. Oxygen has a weaker bond energy, and fluorine is even weaker. Now why is this? Because we start adding what? Anti-bonding, right? So this whole box up here that we start to fill up as we get to oxygen and beyond are the anti-bonding electrons that we're adding in. So oxygen only has a double bond and is weaker than the bond in nitrogen gas, and fluorine only is going to have a single bond and is therefore going to be even weaker as it forms a bond, easier to break apart. So our MO diagrams do a really good job of explaining all the things that Lewis structures did in terms of how many bonds we're going to have. It doesn't tell us a whole lot about geometry on the surface, but it does help us also explain the idea about magnetism, paramagnetism, and how come something like oxygen gas is paramagnetic. All right. Now, I can't do this demo live here. I don't have access to liquid nitrogen, which I would need to isolate the liquid oxygen, but here is a picture of a bunch of oxygen gas, rather oxygen liquid, that has been collected in this dewar up here, being poured between the poles of a strong magnet. And you can see that oxygen liquid hanging out right here in between. Which is really kind of cool that oxygen, this thing that we breathe, that we certainly don't think of as being magnetic, is in fact paramagnetic. Kind of a neat trick. So here's an example of something we can do with MO theory now, right? So we have N2 and the associated cation, O2 and the associated cation, and can we explain what we're seeing here? Or in other words, how come when I take an electron away from N2, my bond energy gets less stable? But when I take an electron away from O2, my bond energy gets more stable, gets harder to break. Right? What's going on here? Now, to finish this, to figure this out, we have to have some MO diagrams for N and N2 plus, or excuse me, N2 and N2 plus, O2 and O2 plus. So let's take a look at this. Now we know for each nitrogen, we start off with 5 valence electrons. For each oxygen, we get 6, right? So that means that in N2, I should have a total of 10 electrons. All right, so we can say, all right, I'm going to put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so as we mentioned before, I'm going to have a total of 2, 4, 6, 8 bonding electrons. I'm going to have I'm going to have 2 antibonding electrons. So 8 minus 2 times 1/2 is going to give me a bond order of 3. Oxygen, on the other hand, I'm going to start with a total of 12 electrons. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So for oxygen, we're going to have a grand total of 2, 4, 6, 8 bonding electrons. And we're going to have 1, 2, 3, 4 antibonding electrons, right, for a bond order of 2, like we saw on the previous slide. Now the trick for looking at the cations and why N2 is less stable and O2 is more stable is where the electron's coming from. If I remove an electron from N2, where does it come from? It's going to come from the highest energy orbital, which is to say this one here. So I lose one of those electrons. What type of an electron am I losing? I'm losing a bonding electron. So now I go from a bond order of 3 to a bond order of 2.5. In contrast, oxygen is going to lose which electron? It's going to lose one of these pi star 2p electrons. So it's going to have one fewer antibonding electron. We fill all these in like so. So it's going to also have a bond order of 2.5. All right. In nitrogen, we have 2, 4, 6, 7 minus 2 gives us 2.5. Whereas for oxygen, we've got 2, 4, 6, 8 minus 3 times 1/2, getting us to the same overall bond order of 2.5. So nitrogen, as I go to a nitrogen cation, loses a bonding electron. Oxygen loses an antibonding electron. Nitrogen becomes less stable, oxygen becomes more stable because of the type of orbitals that the electrons are in and how they contribute to that overall MO, molecular orbital. The last topic we want to look at for our MO diagrams is heteronuclear diatomic molecules and the little wrinkles that they add. For this example, we're going to look at HF, hydrofluoric acid or hydrogen fluoride. Now, we're going to start off with our 2 different atomic orbitals. Note here that we've got the atomic orbital of hydrogen and the atomic orbital of fluorine. Our atomic orbital of fluorine is our 1s electron. Our atomic orbital for fluorine is our 2p electron. All right, now you might note at first, hey, how come the 2p orbital looks like it's lower energy than the 1s orbital here? That's because the electrons in it at this point are around an atom with a higher effective nuclear charge. All right. In fact, our 2s orbital is way down here. We're not even really going to deal with that and where that's going to end up. It's going to be a non-bonding orbital as well. All right, so here we're going to have 3 different types of orbitals. Now we've got our sigma orbital, right? Since it's a mix of a 1s and a 2p, we don't call it sigma 1s or sigma 2p, it's just sigma. And then we've got sigma star up here. Now we've got 1 electron we can take from hydrogen. We're going to take that 1 unpaired electron from fluorine, and we're going to dump those down into our sigma orbital. We have no electrons left to put up here because in the middle we have a new type of orbital, which is a non-bonding molecular orbital. This is where we're going to stick some of our lone pairs. And as we see that these electrons are closer in energy to fluorine, those lone pairs are going to live on fluorine, as is the lone pair from the 2s orbital that we can't even see. And this also supports our idea about electronegativity. The bonding orbital for our electrons is closer in energy to fluorine, so the bond polarity lies towards fluorine. So this image here, this little representation of our molecular orbital, really helps explain and give sort of a theoretical backbone to electronegativity and why particular atoms get lone pairs, things that we just sort of hand-waved a little bit when we talked about Lewis structures, right? We talked about bond polarity and VSEPR, and okay, yeah, this bond's polar because. Here's why it is, right? When we form these molecular orbitals, when we form these spaces where the electrons interact over the molecule, these electrons are closer in energy to fluorine than they are to hydrogen, so hydrogen gets to hold on to them. Right, now you may remember at this point, way back in chapter, I guess it was only way back in chapter 10, we looked at NO, which had an odd number of electrons. And you might remember that when we drew the Lewis structure for that, we had, let's see, 2 resonance structures. And the question was, in this set of resonance structures, which atom had the unpaired electron, right, since we had an odd number of electrons. And we said at the time, all right, this is going to be our major resonance structure. This one's going to be minor because we want to put our unpaired electron on the least electronegative atom. Right? In this case, we explained this with formal charge. Right? This one has a formal charge of negative and positive. We didn't want to put a positive formal charge on the more electronegative atom. So we said this one was our major. But our MO diagram helps us explain that even better. All right, so if we build this heteronuclear molecular orbital diagram, all right, so these two we're going to see all our 2s orbitals, right? Again, oxygen, a little more electronegative, a little higher effective nuclear charge. This is a little bit lower in energy. The nitrogen's a little bit higher in energy. We fill up our sigma 2s and our sigma star 2s. Here we're going to default to the mixing, since nitrogen can mix its levels. So we now have our pi 2p, our sigma 2p, and our our pi star 2p. We fill those up from bottom to top. We have our one unpaired electron up here in our pi star 2p antibonding orbital. Which element is that closest to? It's closest in energy to nitrogen. So which element gets the unpaired electron? Nitrogen gets the unpaired electron. Oxygen gets to have all the pairs of electrons. All right, so this also helps us clear up confusion about resonance. Right, our bond order is greater than 2. Our molecular orbital shows that we actually have 2.5 in terms of our bond order. That's going to bring us to the end of looking at our heteronuclear diatomic molecules in terms of our molecular orbital diagrams. We're actually going to finish up with MO diagrams now. We have one more thing to discuss in the final video, which was looking at resonance a little bit more and how our concepts of pi bonds and sigma bonds plays together with that. So I'll see you there, and until then, take care.